Welcome back, class. In the previous lecture we understood conduction and conductance, which shows how much charges are being transferred for the applied energy. That was the reason why conductance was current upon EMF. However, we must see a broader picture here.
What broader picture, Professor?
You see, students, electrons require a material called as a conductor to flow. That is why the energy transfer is called as conduction. Conductors are made up of metals. We all know that materials are primarily made up of atoms, and these atoms are composed of electrons, protons, and neutrons. We know from the first lecture that electrons and protons attract each other, but we must also understand that electrons also oppose other electrons as they have the same type of charge. So, if some amount of current is flowing through a conductor, which is nothing but flow of electrons, the already present electrons inside the material will oppose the flowing electrons. This opposition is called as resistance.
But sir, what makes metals so special that only they are conductors?
The answer to that can be linked to resistance as well. As mentioned earlier, the already present electrons oppose the flow of incoming electrons. However, metals have a small number of valence electrons and hence provide less amount of opposition. The more valence electrons a material has, the more opposition it would provide, and hence it would provide a higher resistance. Hence, material with a large number of valence electrons are called as insulators, as they insulate or do not allow the flow of electrons. So yes, almost every material provides resistance, but metals or conductors provides less resistance because of the smaller number of valence electrons. On the other hand, insulators provide so much opposition that conduction for them is near impossible. This is also the reason why the wires are usually made up of metals like copper. Now, as we do in all lectures, we need some quantification method of the physical phenomenon we are studying. Here, we would somehow quantify the resistance. As mentioned earlier, electrons generate opposition. So, the longer the conductor would be, the greater the number of atoms it would come across, and greater the number of electrons it would come across, which will oppose the flow of current. Therefore, we can say that the longer the conductor would be, the higher the resistance it would provide. Hence, we can easily say that resistance is directly proportional to length. On the other hand, an electron can technically avoid opposition if it does not come across an atom and if it somehow flows between two atoms.
But sir, end metal is dense and the distance between the two atoms is very small. So how would it fit between the two atoms?
Yes, you see, students, in comparison of the entire atom, the electron is very much smaller than the overall size of the atom and hence can easily slip between two atoms. So, the wider the conductor would be, the more amount of spaces it has to slip through. So, we can easily postulate that the larger the area, the less the resistance the material would provide. Hence, the area of a material is inversely proportional to the resistance it offers. But we must come back to our initial point that electrons are the particles that are responsible for this opposition. And since every material has a different number of electrons, every material will have a unique resistance even though two conductors of different materials have same length and area. This unique property of materials is called as resistivity. As a result, we can define resistance as resistivity into length upon area. Thank you for watching Learning on the Way. If you like the video or if you have learned anything new, please click the subscribe button and like and share the video. If you have any doubt, visit our previous lectures or comment below. Thank you.